Okay, let's look at the homework in Chapter 8 and Chapter 9. Chapter 8, we're going to look at 812 and 813. 812, there are 1, 2, 3, 4, A, B, C, 8, it's 3 actually, A, B, and C parts of it. And the question is, what happens or what are the chances of different ways you could have two children? And this is a small enough set that we can actually list out all the possibilities. For two children, we could have a boy and a boy and a girl and a boy, and a girl and a girl. And you will notice indeed that some of those are the same results. So, for example, the second and third cases, you still get one of each, but there are two ways that can happen, and that's reflected in the question. Well, I'll ask for that. I'll add a question to this probably and ask for that. So, one question, the first question is, what are the chances you can get a boy and a boy? Out of 4 options, there's only one way that can happen, so 1 out of 4. Or you can look at it this way. The chance of getting a boy the first time, you have to get a boy the first time and the second time. And, remember the and rule we talked about. So the chance of getting a boy the first time is 1/2. And means we do what mathematically? And means we multiply. So we've got a boy the first time. What's the chance of getting a boy the second time? Also 1/2. So the chance of getting 2 boys is 1/2 times 1/2, or the same 1/4 we got a minute ago. The second question asks for the chance of getting 2 girls. Pardon me while I work this out. There. It's the same calculation because the probability of getting a girl the first time is 1/2, and, meaning multiply, the probability of getting a girl the second time is also 1/2, which is 1/4, or of the 4 possibilities, 1 out of 4 of those is getting 2 girls. The part C asks, what's the probability of getting essentially the same gender, 2 boys or 2 girls? Well, we can look at this 2 ways also. The easy way to look at it is the list we've made. Out of these 4 possibilities, how many of those are the ones we're talking about, 2 boys or 2 girls? 2 out of the 4. Or 1/2. The other way you can look at it is and this is the easy way, like I say, but the other way you can look at it is in terms of conditional probability. Conditional probability means your first child is one gender or the other, right? It's either a boy or a girl. Whichever it is, let's say your first child's a boy, the chances would be of getting both genders, it's got to be a boy, so that's a 1/2 chance. Or if the first child's a girl, that's the condition on the probability. The second thing would be the probability of getting a girl the second time, which is got to be 1 out of half. So whatever the first one is, the probability of getting the same one the second is going to be 1/2 either way. The same 1/2 we've got here. I said I would add a question, and that was the question about what's the probability of getting one of each? Well, that's the probability of getting the same of each. Also 1/2. 2 out of 4 reduces down to 1/2. Same thing, you can also look at this conditional probability wise too. If you've got whichever you have on the first one, the probability of getting the opposite is still 1 out of 2. And that's what's got to happen for this to happen where you have 1 out of each gender. Questions on chapter on yeah, chapter 8, part the 12, part 12. Is that okay? Well, if that wasn't okay enough, let's talk about if we have 3 children. And again, this is still small enough we can list them all, but we're going to do it both ways. We're going to do it the way we're going to pick out from the list, and also just the calculation way. So with 3, we get a boy, 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 boy. Don't let me miss any of these things, please. Girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, girl. Lost track here. Girl, boy, and girl, girl, girl. Is that 1, 2, 3, 4, 5, 6, 7? Yeah, the 8 possibilities. Hey, you know how you can get 8? You know how you know there are 8 possibilities? Because there are 2 ways to get one kind of child. 2 ways to get the first child. Then 2 to get the second child. Then 2 to get the third child. So 2 to the third power is 8. So we know there are 8 possibilities. If we were looking at having 4 children, that would be 2 to the 4th power, which would be 16 ways. And that gets to the point where I don't want to write all these things out. So let's look at this again. 2 ways. We'll count and we'll do the math. Count and calculate. First question, 3 boys. Only 1 out of 8 is going to give us 3 boys. Or, first child's a boy, and multiply, the second child's a boy, and multiply, the third child's a boy. That's still 1 out of 8. Well, you can, as long as I know which way you're coming from. Really, I prefer the calculations because these numbers are artificially small, and with your real numbers, you know, we're not going to be able to list everything out. I could ask something like, what could be the gender distribution of your class of 30 students? You don't want to write that out. Is that sample of all the sample possible sampling error, the mean, and all. 3 girls, same thing. You got to get a girl, and a girl, and a girl. Or again, only one of these ways. Only one of these ways is going to give you 3 girls. That's 1 out of 8. First one has to be a girl. It's 1/2 times the second one being a girl, 1/2, and times the third one being a girl, 1/2. That's still 1/8. So A and B look the same. The answer to each are 1/8. Either 3 boys or 3 girls. Hey, there's the word or. So what does or tell us to do? So let's do the calculation verse this time. We're going to add. What's the chance of getting 3 boys? We just figured it out. It's 1/8. Or means we add the chance of getting 3 girls, which is 1/8. So the chance of getting 3 of the same gender are 1/4. And there are 2 ways to do it. 2 out of 8 ways is 1/4. The first way, boy, 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 and the last way, girl, girl, girl. There are 2 of those out of 8 possibilities. That's still 1/4. But calculation-wise, it's 1/8 plus 1/8 because it's an or. And the last one is neither 3 boys or 3 girls. Well, if we figured out the way to get of getting 3 boys or 3 girls is 1/4, what's the probability of that not happening? 3/4, which would be these 6 possibilities out of 8. The question was, is it okay if you did a subtraction? That's essentially what I did here. Yeah, I said 8/8 minus 2/8, essentially. That's the same as 1 minus 1/4. So yeah, the calculation works either way there. Okay, any other questions about the stuff in Chapter 8, the probability problems in Chapter 8? And again, let me mention, I'm stressing probability because statistics is based on probability. Statement I made the very first night in class is that our research, this kind of research, doesn't prove anything. That's because there's always a chance of being wrong. What's the probability of being wrong? And therefore, likewise, what's the probability of being correct? So we understand a little something about probability, meaning that I don't know for a fact that A is larger than B, or that Miss A's class scores higher than are better math students than Miss B's class. I don't know that for sure, but I can know to what degree that's likely, what the probability is. So that's why I stress probability for, half of a short lesson. So reasonably okay with that? Everybody equally confused? Okay. Then let's look at the stuff on Chapter 9. And some of you are telling me just how worn out you are by these true-false questions. And that's because these questions have to do with the sampling distribution of the mean, which you were confused from the first time I read the definition to you, and that's okay. Again, I just asked you to follow. I didn't ask you to necessarily be able to reproduce what we were talking about here, but just follow me. And the point is that I could take any kind of distribution, no matter what shape it was, and if I take all the averages of all the possible averages of a sample, that's a better way of saying it than I think. If I take the average of all the averages you might have gotten of all the possible samples, that's going to be the same as the average of the initial population, the initial population, and it's also going to be normally distributed. So let's look at page 206. Again, these are all true-false questions. So I'm just going to talk through these. I don't have anything I'm going to show you to write down or anything, so just, again, follow me as we talk through them. 9.6 starts saying that the random sample tends not to be an exact replica of its parent population. That means the sample probably doesn't look like the population. And this has a number of implications. True or false? All possible let's try again, Don. All possible random samples can include a few samples that are exact replicas of the population. Most aren't. It just got through telling you that. Most samples don't look like the population. Some do. It gets back to my illustration. If you flip a coin 50 times, you expect 25 heads, 25 tails. You're probably not going to get that exactly. You're probably going to get close to it, though. So your random sample, is probably going to look reasonably close to the population. But the answer to A is, and feel free to type true or false or say true or false when I'm talking about these. The statement is, most of the samples aren't exact. That's true. Most of them are not exact replicas. That's true. B, a more representative sample can be obtained by hand-picking observations rather than randomly. No, because if you hand-pick, you're going to skew it one way or the other, probably unintentionally, but it's not going to be random, so it's probably not as likely to look. Now, we did talk about things like stratifying samples. That's not the same thing as hand-picking, but that's just controlling the proportions. C, as far as it misrepresents the parent population, the random sample can cause an erroneous generalization. Paraphrase, real language. You've got a random sample, it might be wrong. It may be wrong, that's true. You might happen to pick, if you've got a population of 100, and you want to know what the mean is, again, this is an artificially small population because you could deal with 100. But let's say you had 100 students and 100 test scores. You randomly pick 10. What are the chances of the mean of those 10 being exactly the same as the mean of the 100? It's probably not going to be. Is it possible that you pick the highest 10? And that is possible, but not likely. Likewise, you could have picked the lowest 10, or even maybe most of them in the lower half. That could happen. So the point is that your sample, because you're just collecting a sample, it can be wrong. That's why we have these p-values we talked about. What's your probability of being wrong? In practice, well, this is a good one. In practice, the mean of a single random sample is evaluated relative to the variability of means for all possible random samples. Let me paraphrase that. Paraphrasing that. Variability matters, true or false? Spread outness matters, and the answer is yes, it does. Okay. 9.8 is also true, false, 9.8, and this refers to the sampling distribution of the mean. Now, keep in mind, again, follow me on this. The sampling distribution of the mean is all possible ways you could get samples from a given sample size. If I had that population of 100 and I'm selecting samples of 10, what are all the ways I can get a sample of 10? And the answer is a bunch. Okay, so that's the first thing I asked. The sampling distribution of the mean is always constructed from scratch, even when the population is large. By constructed from scratch, it means I'm always going to list all of them out. And, oh, not just no. False. B, the sampling distribution of the mean serves as a bridge to aid generalizations from a sample to a population. Paraphrase, that means we're going to take the sample, see what the sample looks like, and decide what the likelihood is that looks like, that does indeed describe the population. That's true. That's why we take the sample. We want to learn something about the population. Sampling distribution of the mean is the same as the sample mean. The answer is no, because you get a bunch of different sample means. D, the sampling distribution of the means, always reflects the shape of the underlying population. Now that sounds a little tricky. It's not a trick question. It's a little bit loaded, but if we understand what it means, I think we'll understand why the answer is what the answer is. What does the sampling distribution of the mean always look like? It's always normal. But is the population always normal? No. Therefore, no, it does not necessarily reflect the shape of the population of the mean. This is why we can use stuff we know about the normal curve for a distribution that's not normal in itself. E, the sampling distribution of the mean has a mean that always coincides with the population mean. Again, that's like the average of all the possible averages. Well, the average of all the possible averages is going to be the same as the average of the mean. We saw that with that little 16 possibility models that we ran from earlier in the text here. F, sampling distribution of the mean, is a device used to determine the effective variability. That is what can happen just by chance when samples are random. Yes, variability matters, and yes, the random samples may or may not look like the population. That's true. But variability matters. And we'll see that more and more as we look at some other specific kinds of procedures. G, the sampling distribution of the mean remains unchanged even when with shifts to a new population or sample size. Now, if you go to a new population or new sample size, you're going to get different data. It's not going to look the same as that necessarily. Probably not going to, so that's false. H, the sampling distribution of the mean supplies a spectrum of possibilities against which to evaluate the observed sample mean. That just, how do I paraphrase this? You get different samples. Again, if you get enough different samples, The more you get, the more it looks like the population. But yes, that's true. Last one, finally, the sampling distribution of the mean tends to cluster more closely about the population and mean with increases in sample size. Paraphrasing, the larger your sample is, the more your sample probably looks like the mean. Yes, a larger sample size is going to be more likely to look like the initial distribution or the population. Okay, I'm happy if you could follow most of those, because this isn't going to be like a big test item, but it's important to kind of cover this ground, because when we do things a little later in the course, you might be tempted, I hope you are tempted, to say, well, why do we do it this way? What difference does it make? And this lays the foundation for that, and I can, if I need to, I can refer back to what you remember. The larger the sample size, the more it looked like the mean, so larger sample size is better, again, to a point. I'll say things like that and refer back to this law. Any other thoughts, questions, or comments about this section, or either section? Okay.